In this video, we're going to revisit the mass mole calculations that we would have had previously. The difference with what we did before and what we do now is the actual steps that we do is not different at all. The only difference is instead of doing a calculation for sodium or calcium, it's now for Na2SO4 or C2H4OH. But the steps are exactly the same. The second thing that we're going to talk about is percent composition calculation. So let's say we got a chemical. Well, what percentage of that chemical is carbon? What percentage of that chemical is sodium or oxygen? And this second piece here is actually pretty simple. There's really nothing new we got to do except do a percent calculation. So it's pretty simple. All right, so review. Back in chapter 3, we talked about mass to moles to number of atoms. Well, mass to moles. We use molar masses. We look them up on the periodic table. No big deal. Moles to atoms, we used Avogadro's number. Okay, 6.022 times 10 to the 23rd. When we first learned Avogadro's number, we said, well, it doesn't just apply to atoms. It's like 1 dozen. 1 dozen refers to 12 of anything. A dozen cookies, a dozen cars, a dozen baseballs, a dozen calculators. Well, Avogadro's number applies the same thing. It could mean this many atoms, this many molecules, this many formula units. Okay, remember formula units is the correct name given to the structure of an ionic compound. Doesn't matter. It's the same calculation. So if you need to, a lot of review of 3.3. All right, so here's our review question. Let's say you had 33 grams of copper. How many actual atoms would you have? So what I'm going to do, I'm going to pause it real quick review on the spot, and figure out this calculation and see if you got what I... Okay, so your final answer should be 3.1 times 10 to the 23rd atoms of copper. So if you got 33 grams of copper, that's how many atoms of copper you had. Again, complete review from chapter 3, section 3. So, well, how does this apply into chapter 7? Well, instead of 33 grams of copper, here's what we're going to have. You have 33 grams of copper 1 sulfate. How many formula units do you have, or how many structures do you have? Remember, formula units, atoms, molecules, they're all the same thing, just like cookies, cars, calculators. Avogadro's number applies the same way. Here's what the difficult piece is. Those are all formulas of copper, sulfur, and oxygen. Which one's the correct one for copper 1 sulfate? Because you need the correct one to get the right molar mass for the calculation. If you don't have the right formula, you're not going to have the right molar mass. If you don't have the right molar mass, you're not going to do the right calculation. So again, here's where you've got to know nomenclature to do any of the calculations. So copper 1 sulfate. Remember, copper Roman numeral 1 tells us not 1 for the subscript, but 1 is the charge. Then you got sulfate, you've got to remember, is SO4. Sulfate is an O4, and it has a 2 minus charge. So copper bonded to sulfate, copper 1 sulfate, is Cu2SO4. So the formula we're looking for is right here, Cu2SO4. Now we can do our calculation. Okay. So what I want you to do, I'm going to pause this. Knowing that it's now copper sulfate, Cu2SO4, figure out how many formula units there are. Okay, so pause it, figure that one out. Okay, so here's the calculation setup for solving for 33 grams of copper 1 sulfate. Again, steps are identical. Grams of copper sulfate multiplied by 1 over the molar mass. Grams cancel. 1 mole of copper sulfate multiplied by Avogadro's number. Moles of copper sulfate are gone. If you look at the two copper examples, they're identical. The only difference is the molar mass. Okay? Now, still use Avogadro's number because this is not an atom anymore. Okay? It's also not a molecule. A molecule is a name given to a covalent structure. That's not covalent. Why is it not covalent? There's a metal in it. So it's still the same calculation. We just use a different word to describe its structure. Okay? All right, so what I've got here, two last ones to do. This is going, one's going each direction here. So I start out with the number of molecules of carbon dioxide. Now, I put atoms up there just to remember it's the same type of calculation. Okay, we use the word molecules because it's a covalent compound. So go molecules back to mass. And then in the second one here, I've got 3.2 kilograms of iron 2 nitrate. And you're going to number of formula units, which is, again, same thing as solving for atoms. So I want you to work on these two, pause it, and then I'll show you answers, and you can kind of check your work. All right, so if we look at the first one here, you got 9.4 times 10 to the 22nd molecules of carbon dioxide multiplied by 1 over Avogadro's number, multiplied by the molar mass, which is 44.01, or again, whatever periodic table you have. Final answer, 6.9 grams of copper, or I'm sorry, of carbon dioxide. It's definitely not copper. The 3.2 kilograms of iron 2 nitrate, solving for the number of formula units, which is similar to solving for the number of atoms. First thing, iron 2 nitrate, iron Roman numeral 2, iron 2 plus. Nitrate, you got to know, is NO3, and it has a -1 charge. So, Fe2 plus, NO3 minus, makes FeNO32. Now that you have a formula, you now have a molar mass, 179.857. You got a molar mass. Now you can do the calculations. 3.2 kilograms of iron 2 nitrate. Don't get caught. That's kilograms. You got to change it to grams, 3,200. 3,200 grams of iron nitrate multiplied by 1 over its molar mass. Okay. Again, write it out. Got kind of sloppy there on a little bit of the formulas. Grams cancel. Moles cancel. Multiply by Avogadro's number, and you get 1.1 times 10 to the 25th formula units of iron 2 nitrate. So again, only did a couple examples, but there's nothing different than what we did before, other than recognizing that you now don't just have one element that you have to look up on the periodic table. You have to look up an entire chemical full of elements. Okay. The next thing that we'll talk about here in a little bit will be percent composition. One last thing here I want to talk about in terms of mass mole stuff. Now that we're dealing with an entire chemical, we got to kind of throw in one other little piece here. It's not a difficult concept, but people have a tough time just doing this counting because we're talking about atoms and things like that. So first of all, just nothing on paper here. Just answer this question that I'm telling you right now. If you have 12 cars, how many tires would you have in those 12 cars? Well, assuming they all have tires, 12 times 4, 48. Correct. If you had 12 bicycles, okay, not tricycles, not unicycles, but 12 regular bicycles, you would have 24 tires. So we're multiplying how many pieces or how many objects are in that structure. That's what I want you to carry over into this example here. So we start out with, if I say you have in your hand 12 Cu2SO4s, actually in your hand, and you were able to count them, how many actual coppers would you have? How many actual sulfurs would you have? And how many actual oxygens would you have? Okay, so take a second there. If you actually had in your hand 12 Cu2SO4s, how many coppers would you actually count? How many sulfurs? How many oxygens? Well, hopefully everybody would say, oh, well, if I count out, I'm going to have 24 coppers in my hand. I'm going to have 12 sulfurs, and I'm going to have 48 oxygens. That's what I'm going to count out, and that's correct. Now, let's do one more thing. Let's say I have 24 copper sulfates in my hand, just like 24 bicycles or 24 cars. Don't count the individual pieces. Keep the word dozen. Well, how many coppers would I have? Well, if I've got 24 Cu2SO4s, I actually have 4 dozen copper atoms, right? Dozens 12. I've got 2 dozen, so I really have 24 copper sulfates. So if I really got 24 of those, and in each one there's 2 coppers, got 48, which is 4 dozen. I'm going to have 2 dozen sulfurs, and I'm going to have 8 dozen oxygens. Again, not a new counting system or anything like that. It's just I want you to count these in terms of dozens and not individual pieces, because this is going to be important as we carry it down to chemistry numbers. Now let's say I have 6.022 times 10 to the 23rd Cu2SO4s in your hand. So you're able to actually hold that many in your hand, which really that's not a ton. That, not a ton. It's only a couple hundred grams, so you could probably do that. Well, how many actual coppers do you have? Well, you have 2 times 6.022 times 10 to the 23rd. How many sulfurs do you have? You actually have 6.022 times 10 to the 23rd. How many oxygens do you have? Well, 4 times 6.022 times 10 to the 23rd. Again, you see how we just multiplied that out. Whether we say 12 or 6.022 times 10 to the 23rd copper sulfates, we count them the same way. Now, last one here, and this is the one that people kind of have issues with. Up here I said 2 dozen Cu2SO4s. What if I had 1 mole of Cu2SO4s? Think of the mole as a counting unit. Again, apply it the same way as if this would say 1 dozen. If I have 1 mole of Cu2SO4s in my hand, or say 1 dozen, how many coppers do I have? I would actually have 2 moles of copper in my hand. Again, think about this. If I have a dozen bicycles, how many tires do I have? 2 dozen, right? 12 bicycles, 24 tires. 1 dozen bicycles, 2 dozen tires. 1 mole of copper Cu2SO4, 2 moles of copper. How much sulfur do I have? 1 mole. How much oxygen do I have? 4 moles. Okay. Now, it seems kind of confusing, and maybe after this you're like, you know what, I'm not sure I even know what you're talking about now because it's confusing. It's just because we're using the word dozen and moles. And this might be something, we kind of have to talk about in class at some point, but we can definitely work through this. This is something, we've got to just work through. It's not hard math or difficult math. We just get confused because now we're using the word mole a lot, and we think it's different than dozen, but it really isn't. The next thing we will get into then is looking at percent composition calculations. In this last video, we're looking at the percent composition calculation for a particular chemical. Basically, when we talk about percent composition, we first have to define what is the measurement we're making. In this case, we're talking about the percent composition by mass. So when we talk about this, what we're looking at is what is the mass of an element present in an entire compound. So what is the percentage of carbon in something like CO2? Or what is the percentage of sodium in something like NaCl? How much sodium is in salt? How much carbon's in carbon dioxide? This comes back to the law of definite composition, which we talked about in Chapter 3. Real simple. All we basically do is use molar masses. Okay? So, here's our calculation. It's a simple percentage. What is the total molar mass of a given element divided by the total molar mass of a compound? Multiply it by 100, and that is the percentage of an element that's in a compound. So if we want to find what is the percentage of sodium in sodium chloride, we take the molar mass of sodium, divide it by the molar mass of salt, times it by 100. That gives us the percentage of sodium in NaCl. Now let's say we wanted to find the percentage of oxygen in carbon dioxide. Well, now we take the molar mass of O2 divided by the molar mass of CO2. Now, here's the thing we got to pay attention to. It's the molar mass of O2. So it's not just one oxygen we're taking into account, it's 2 oxygens. So we'd have the molar mass of 2 oxygens divided by the molar mass of CO2 times 100 gives us the percent of oxygen in CO2. Okay, so again, we have in CO2 we have 2 oxygen, so what is the percentage? Is it 70% oxygen? Is it 80% oxygen? Is it 20% oxygen? You can make some pretty quick observations just by simply knowing molar masses. Each oxygen is 16, so 16 and 16 is 32, compared to a carbon atom which is only 12. So 16 out of 12 plus 16 plus 16. So you can kind of in your head at least do some approximating or estimating. So that's all it really is. If they want to know a particular element, then you can solve for what that percentage is. Now, let's say we want to actually determine actual amounts. So you measure out a real amount of a chemical. So let's say we have, well, what if I have 10.2 grams of salt? How many grams are just sodium and how many grams are just chlorine? Well, it's a two-step problem. The first step is we got to figure out what's the percent composition. What is the percentage of sodium and what is the percentage of chlorine that are in NaCl? Then what you're going to do is apply the percentages of sodium and the percentage of chlorine to 10.2 grams. Okay. And now we can say out of the 10.2 grams, for example, hypothetically 7.3 grams are from sodium, 3.0 grams are from chlorine, or whatever the case may be. But again, in this case, we have a two-step problem. If we want to find out, again, actual amounts, okay, real amounts that are given to you, we need to first calculate what the theoretical percentage would be. And where does that come? That comes from molar masses, and that comes from the formulas. Okay? So again, is this a huge calculation right now? No, but it will become significant when we get into other things in section 4 of this chapter, as well as other calculations down the road. So pretty simple thing, but again, until you do a couple examples, may be a little bit confusing, but in most cases it looks harder than what it really is.